Good afternoon. I welcome you to this session of IC Engine, and today we will try to discuss about an important aspect of internal combustion engine operation, that is the transport of heat. So, if we try to recall that for the SI engine and CI engine combustion, we have discussed many issues and we have seen that combustion, which is the manifestation of combustion is the appearance of a visible flame, or if we try to measure, then of course rise in pressure. So, we have seen that whether it is SI engine or if it is a CI engine, essentially combustion is nothing but the process of transforming energy from one form to the other form. And we have understood that we are supplying, rather we need to supply fuel with air, we need to supply rather homogeneous mixture of air and fuel if it is SI engine, and for the CI engine we have seen that we are supplying air and the supplied air is now compressed, and towards the end of the compression stroke fuel is injected into the cylinder by a fuel nozzle. So, basically what is done, the fuel we have discussed that is a family of hydrocarbon. So, the hydrocarbon, in fact the fuel in which chemical energy is stored, and the stored chemical energy is converted into the another form of energy in the form of heat, and this is done by a process which is known as the combustion. So, combustion means the chemical energy of the fuel is combustion process is initiated, is allowed to occur inside the engine cylinder, essentially to convert chemical energy of the fuel into the another energy in the form of heat, rather heat energy. So, if we try to recall that hydrocarbon, if I try to write CXHY, in fact today I will try to discuss about the heat transfer and energy distribution. So, that means if we try to write CX, that is the hydrocarbon, we need to mix this fuel, in the gaseous state, and it is now allowed to react with the oxygen present or available in the supplied air, and we get so this heat is generated, temperature which is generated because of this reaction, this is an exothermic reaction, and because of this temperature heat we create thrust on the piston face and engine is running. So, this is what we have understood from the CI and SI engine combustion processes, that is what we have discussed in the last lectures. Now, question is the amount of heat which is being generated because of this combustion reaction, is it possible that the heat which is developed can be transformed equally into the available work? That means what I would like to say, we are using input energy, of course that is remaining stored, that is the internal energy of the fuel, chemical energy of the fuel which is remaining stored in the fuel, that energy is now converted into other form and if we can convert equally, that is if the all chemical energy can be converted into the heat energy, if we can convert, then next question is, can we utilize the energy which is being generated to an equivalent amount of work that we will be getting from the engine. So, this Q heat which is developed, we have seen that most of the engines are having efficiency which is around 50%, 55%. Now, that means the energy, to be precise heat energy which is produced, we cannot transform this energy into the equivalent amount of work. That means somewhat amount of energy, somewhat amount of heat is getting transformed, is getting transferred from the engine cylinder or different other parts of the engine to the other places. So, today we will try to see that when we talk about energy which is being generated, a part of the energy is utilized to convert into the equivalent amount of work, whereas remaining part of the energy is getting transferred to the other parts in different forms. So, we will discuss that the how much, there may be, if we consider that chemical energy is getting converted, because we know from our school days understanding that energy cannot be destroyed, energy cannot be created. So, energy is now transformed from one form to the other form. So, chemical energy is getting transformed to the heat energy, but the heat energy which is being generated, we cannot utilize all the heat energy into the equivalent amount of work. So, now I will write that the amount of heat which is being produced, how much portion of that heat is utilized to that is available at the shaft, and how much portion of the energy is transferred to the ambience or is lost, to be precise. So, the part of the energy we are using, we can extract to drive our drive the vehicle, that is the available work we are getting at the shaft, while remaining part of the produced heat is getting lost. So, we need to know, when we are talking about energy is getting lost, of course, heat will transform from one place to other, and we know from our undergraduate heat transfer course that when heat is being transferred from one place to other, heat needs to be transferred either by conduction or by convection or by radiation mode. So, now we will write that heat transfer. So, see this amount of heat which is being transferred, right? Rather, we will try to write heat distribution. In fact, I can write energy distribution. Right. So, we know that we are getting only shaft work, and that is nothing but, so if we try to draw the schematic, if it is 4-stroke cycle CI engine, then we will have fuel nozzle and this crank will be rotating. So, the amount of work which is produced, which is available on the piston face. So, this is the amount of work available at the piston face. That is nothing but mass flow rate of fuel into calorific value of the fuel or heating value of the fuel, but out of this amount we are getting only a part at the shaft, and which is that part? So, if we know that the shaft work W shaft which is available at the crankshaft, that is nothing but eta brake thermal efficiency, that is what we have m dot fuel, calorific value of fuel, and of course we have to multiply it by another factor that we know, that is the combustion efficiency. So, this is the amount of work we are getting at the shaft. That means this expression indicates that the work which is being produced at the piston face is not available at the crankshaft. So, some part of the work is nothing but, again if we try to recall our first law of thermodynamics. So, this is different form of energy. So, we have energy that is in the form of heat which is being produced because of this combustion reaction, and we are getting different other form of energy at the shaft, that is work. So, this heat is converted into work, but all this heat is not getting converted into the work, and that is why you are getting less amount of work at the shaft. So, that means part of the work is getting lost. Maybe part of the work is getting lost not because of this transform of heat from the cylinder walls into the ambience, but of course there are different other parasitic loads. So, that means if we try to write that power developed can be broken into different parts. One is the brake power plus Q dot exhaust plus Q dot loss plus of course parasitic load. That means total power developed can be broken into 4 different parts. First one is the brake power that we are getting at the shaft. Second is the exhaust loss that we know. If we try to recall that in a 4-stroke cycle, whether it is SI or CI engine, a part of the combustion gases, rather I can say a small portion of the combustion gas is taken through the exhaust blowdown, so that the piston will encounter a relatively lesser resistance during its travel from the BDC to the TDC during the exhaust stroke. So, that is, so when part of the combustion gas is leaving without doing work, that means the enthalpy is getting lost. So, the exhaust gas is leaving from the cylinder, and that is done essentially to reduce the resistance that the piston will encounter during its travel from BDC to TDC during exhaust stroke, and while the gas is leaving it will carry enthalpy with, and so that enthalpy we are not utilizing, so that is getting lost. So, this is the exhaust loss. So, exhaust heat transfer. There will be some amount of heat loss, that is, we know that if we try to recall, maybe in the beginning of my lecture we have not today, in the beginning of this course I introduced the nomenclature of different parts of the internal combustion engine, and from that schematic depiction if we try to recall that we had one cooling water jacket. The cooling water jacket is provided, that is coolant is needed to be supplied to reduce the temperature. So, Q loss will be there. So, some portion of the heat will be lost through the coolant, and there are other different sources that we will discuss today. And of course, the parasitic load we have discussed in detail, that when we need to extract energy from the energy which is being produced by the internal combustion engine, essentially to run different auxiliary parts, like we will discuss that pump of the radiator, then other if we need to supply say fuel pump, so part of the energy will be utilized to run the pump which is being supplied fuel into the nozzle. So these are the parasitic loads, and to run these auxiliary parts, auxiliary systems, we need to extract, we need to borrow energy from the energy which is being developed. So this is the different parts. So now at least what we have discussed today, this is of course qualitative, we know, and this is true, this is obvious that the brake power will be definitely lesser than the power being developed, that is why brake power efficiency will be less. So the different components we have discussed today, and those are qualitative. So we need to know what is the quantitative value of each and every part, that is what we have written in the right hand side. So the Q exhaust is near about 20 to 45%. That means if we consider the total power developed is 100%, 20 to 45% of the total power will be lost in the form of heat into the surroundings. So this is lost energy. So we can, so from this, at least from this expression, we can really understand that efficiency of the internal combustion engine cannot be more than 60%. Then of course brake power, that is very important. Brake power, that is 25 to 40%. Then Q loss will be equal to 10 to 30%, and parasitic load, and the parasitic load, that is we need to know that how much percentage of the total getting lost, that will be near about say 5%. So this is the rough estimate, at least a quantitative estimate, to know that how much percentage of the total power will be required to run this, or will be required to will be lost, will be available, and will be required to run the parasitic system, parasitic load. So this is the rough estimate. So we have understood that the loss exhaust is 20 to 45%. So loss is basis, and Q exhaust loss is 20 to 45%, and loss of heat is around 10 to 35%. So now at least we should know now that what are the different losses. So this exhaust loss, we have seen that we take exhaust blow down, and when we are taking exhaust blow down, some enthalpy is getting lost. So this enthalpy cannot be utilized to as the useful energy. So this is what we have understood. Now from this Q dot loss expression, that is loss due to heat transfer. So this loss can be again divided into a few parts. What are the different parts? That is Q dot coolant plus Q dot ambient, and then Q dot oil. So this is the total loss. So now coolant we need to supply. So in this context again I will tell that we need to supply coolant. So knowing fully that supply of coolant, we will try to reduce the heat which is being produced. So that means knowing fully, intentionally we are supplying coolant. Why we are doing so? Because if we do not take away the heat which is being produced in the inside the engine cylinder, then there will be excessive rise in temperature, and because of this temperature different parts of the engine cylinder together with the lubricating system will be start malfunctioning. So the different parts of the engine cylinder will be damaged, together with the lubricating system will start malfunctioning. The lubricating properties will be destroyed, and if the lubricating system start malfunctioning, then it will leads to different problems altogether. So knowing fully that we need to coolant will take away the heat from the engine cylinder, even then we are supplying coolant essentially to maintain temperature level inside the engine cylinder which is suitable for the for the different parts. I mean, different parts can withstand a particular temperature limit. So we need to keep in mind that the temperature limit, the maximum temperature limit that the different parts of the engine cylinder can withstand. So keeping that in mind, also as I said, we need to keep the lubricating system intact. So the temperature should not go very high, so that the properties of the lubricating oil as well as the lubricating system will start malfunctioning. So these are the different things, but at the same time we need to keep in mind that the coolant should not take away substantial amount of heat such that the power output or the thermal performance of the engine will be will reduce drastically. So we need to have a compromise between these two. That means temperature should be taken away from the cylinder essentially to save different parts of the cylinder, along with the to keep the lubricating system intact. On the other hand, we need to keep in mind that the heat transfer should not be very high, otherwise the thermal efficiency of the engine, thermal efficiency of the internal combustion engine will reduce drastically. So this is what is done. So knowing fully that this is what is done, so the Q loss, Q coolant we have understood, fine. Then what about Q ambient? So why Q ambient is important? So this Q dot oil, in fact I can write Q dot coolant, that is heat loss to the coolant, and we have discussed about the merits and demerits. And then Q dot oil I am writing, that is very small, and that is it depends upon the type of oil and engine speed. And Q dot ambient, that is heat loss to the surroundings. So these three we have understood. Now when that means now we need to know that there will be significant portion of heat which is being generated because of the conversion reaction will be lost. Now at least we should know what are the different modes of heat transfer. As we said, rather as we have discussed a few minutes back, that we have studied from our undergraduate heat transfer course that heat can be transferred from one place to other places following three different modes, that is conduction, convection and radiation. So when we talk about heat transfer, in the engine cylinder, then these three different heat transfer, I mean heat is getting transferred from the engine into the ambience following three different modes, that is conduction, then convection and finally radiation. Right. So, these are the three different modes. Now, we have understood at least this, that these three different modes are present to transform or transfer heat from one place to the other places, I mean from engine wall to the combustion gases or vice versa, or engine wall to the surroundings, or from intake manifold to the intake manifold wall to the incoming air, or vice versa. That will depend on that will I mean this transfer mode will follow either conduction or the convection, and we will also see that radiative heat transfer also there in the inside the engine cylinder. So, now we should know what are the different places of heat transfer. Different places where heat transfer takes place. Number one is heat transfer in the intake system. Heat transfer in the intake system, that means either we are taking pure air for the CI engine or we are taking air fuel mixture for the SI engine if it is carbureted engine. Now, heat transfer will take place in the intake system, that means heat will transfer, rather heat will be transferred from the intake manifold wall into the incoming charge, or reverse might be there. It is, we have seen from our understanding we have till now that the intake manifold is used to supply charge, that is fuel air mixture for the SI engine and only air for the CI engine. Now, the temperature of the charge or the incoming air which is drawn into the cylinder during the intake stroke, that plays an important role for the overall rather for the thermal performance of the system. It is advisable to heat up the charge or intake air, and for that sometimes we are using turbocharging, supercharging. Now, this intake manifold temperature is sometimes, I cannot say always, but sometimes becomes higher depending upon the engine design. Since the intake manifold is very because of, if it is close to this I mean it is anyway connected to the engine cylinder, so depending upon their location the temperature of the intake manifold may vary. Now, what will happen, the intake manifold temperature since it is very close to the hot components of the engine, the wall temperature of the intake manifold will be higher, and as a result of which there will be transfer of heat from intake manifold to the incoming charge, and that is T, I can write T charge, right. So, this heat transfer will takes place. Now, when we talk about, rather when we are thinking about, rather when we are discussing about the transfer of heat, so if we can think that the intake manifold temperature, as I said, if it is designed such a way that the temperature of the wall temperature of the intake manifold will be always higher, and that is that may have a few advantageous and disadvantageous features, but at the same time we need to keep in mind that the temperature of the intake manifold, since it is, I mean, if this is anyway connected to the engine cylinder, so the I can say that hot components of the engine compartment. So I mean, if it will behave like a hot component of the engine cylinder if we design properly. Now if that is the case, or even this is not the case, somehow since it is connected to the engine cylinder, so the temperature of the wall of the intake manifold will be higher and heat will flow from wall into the charge if it is SI engine. So the heat transfer into the intake system. So now we are discussing about the heat transfer, different places where heat transfer takes place. So the heat which is taken, the wall temperature of the intake manifold is rather becoming higher while heat is getting lost from the engine cylinder. So the wall temperature will be definitely higher when engine is running continuously. That means at a later a few cycles of the engine operation, later stage, definitely the wall temperature will be higher, and that temperature will come from the engine cylinder. So the heat which is getting lost from the engine cylinder, that will heat up the wall of the intake manifold, and that heat again will be transferred into the charge, and that has a few advantageous feature. I cannot say it will have always advantageous feature, but it is having advantageous feature as well as disadvantageous feature. What is the advantageous feature? Advantageous feature is that since if it is SI engine, if it is carbureted engine, we need to supply air fuel mixture. We need to ensure that fuel which is being supplied with the air will be in the gaseous state. So fuel will start evaporating, vaporize. So the heat which is being transferred from wall to the charge will help for the evaporation process of the fuel itself. So this will in a way help the combustion process to have in a efficient way when the final combustion takes place. I mean the combustion takes place inside the cylinder. On the other hand, it will have disadvantageous feature, in which way? That means the temperature of the air will be increased. So the charge is nothing but the air plus fuel mixture. That is what I told many times. So when heat is being transferred from the wall into the charge, the transferred heat will help the fuel the gaseous fuel to evaporate, and that will help the combustion process. But at the same time, the temperature of the air will be increased. Now if the temperature of the air is increased, then we can say that means what will happen? If the temperature increases, density will decrease. So as a result of which, the volumetric efficiency, that is what we have defined in one of my previous classes, that the volumetric efficiency will be decreased. So again, this is not a good aspect of the engine operation. So maybe the supplied transferred heat from the intake wall again to the charge will help the gaseous fuel to evaporate, and that will in a way help the combustion process to take place in a efficient way. But at the same time, another problem will be there, that the transferred heat into the air will try to, air temperature will increase, and that will if air temperature increase, then the density will change, and that change in density will alter the volumetric efficiency. So now I am writing that this transfer of heat into the charge in the intake manifold has advantageous as well as feature. First of all, the transferred heat from intake manifold wall to the charge will help the fuel to gets vaporized, right, and that is what is needed for the efficient combustion. So this is advantageous feature. So this is the advantage. So I am writing this will help for the better combustion. But disadvantage is that increase in air temperature will reduce the density and which in turn will reduce the volumetric efficiency. As the mass of the air reaching the cylinder will be reduced. So this is the case. So this is having advantage and disadvantage. Fine. Next we need to know heat transfer in the combustion chamber. So next is heat transfer in the combustion chamber. So we have seen that the heat which is getting lost from the engine cylinder into the ambience, but some part of this heat will be utilized to heat up the intake manifold wall, and that is quite obvious. And now that heat will be again transferred into the incoming charge, but this heat transfer from the wall of the intake manifold into the charge is having advantage as well as disadvantage. That is what we have discussed in the last slide. So now we need to know at least what are the different modes of heat transfer in the combustion chamber. So as I said that when we talk about heat transfer either from the intake manifold into the intake manifold wall into the charge, there will be convective transfer and also the conduction transfer. So the heat which is getting lost from the engine cylinder, that will heat up the wall. So that wall will have finite thickness. So within the wall there will be conductive transport of heat, and that heat will be again transferred from the wall into the charge following the convective mode. So that is what. Now heat transfer in the combustion chamber, again in this case as I said, there will be conduction, there will be convection as well as radiation. So this is the case. That means the heat which is being produced from because of this combustion reaction, that heat will not be transferred into the equal amount of work. So the energy will not be transferred, energy will be, energy will not be destroyed. So the heat will not be transferred equally into the work. So part of the heat will be transferred from the engine cylinder. Now if we now try to draw the engine cylinder, say TDC, this is BDC, and piston is moving. So this is the clearance volume and this is a combustion chamber. Now it will definitely create thrust, and because of which we will get shaft work, but a part of the heat will be lost. Now if we try to draw the cylinder wall is having finite thickness. So this is cylinder wall. So this is, say, thickness is D. This is wall of the cylinder, right? And so the temperature which is which will be produced inside the cylinder because of this combustion will be high, and that heat will be now transferred into the wall. The space is filled up with the fluid, and the fluid is moving continuously. So there will be convective transport of heat. So this is, say, Tg gas temperature, this is Tw. That means inside the cylinder we have convective transport of heat which is being developed because of the combustion. Since the piston movement is continuous, because of this movement of the piston we will have kind of movement of the combustion gases or fresh charge inside the cylinder. So there will be kind of flow of combustion gases into the cylinder, and that will leads to the convective transport of heat. So the heat which will be developed, which will be generated in this area initially in the combustion space. So from there will be transfer of heat from transfer of heat to the wall of the cylinder, and that is the convective transport of heat. And as I said, the cylinder wall is having finite thickness. So when the wall will be heated because of this combustion, because of this heat which is being developed because due to the combustion reaction, now there will be conductive transport of heat into the wall, and finally we will have loss of heat into the ambience, that is T ambience. So if it is Tw1, this is Tw2, and Tw2 will be lost into the ambience. So again we will have a convective transport of heat. Not only that, if the wall is surrounded by the cooling water jacket, then again we will supply coolant, so the convective heat will be there, convective transport of heat will be there. So we have understood that conduction is present, convection is present. Not only that, the rise in temperature inside the cylinder because of the combustion is very high, of the order of 3000 Kelvin. So the TAG of the order of 3000 Kelvin. So this high temperature will allow heat transfer to take place following the radiative mode as well. So we cannot trivially ignore the radiative transport of heat because of this high temperature. So we have seen that convective transport of heat will be there because of the movement of the combustion gases. Since the wall of the cylinder is having finite thickness, we cannot ignore the conductive transport of heat. Finally, the heat which is being conducted to the outer wall of the engine cylinder will be again convected into the ambience, and because of this convective transport to the ambience, we have discussed that because of this a loss of heat into the ambience, the intake manifold will be heated off, and that heat again will be transferred into the charge, and finally we have understood that the rise in temperature because of the combustion gas is so high that it will leads to the radiative transport of heat as well as inside the engine cylinder. So that is what we have understood. So these different modes of energy transfer is there, and that is what we have discussed in the beginning of the course. So the amount of heat which is being generated is not getting equally converted into the work. A part of the heat which is being developed we are getting in the form of work, while remaining part of the energy in the form of heat, of course, is getting lost, and is getting lost following three different modes of heat transfer. That is what we have discussed till now. Next is very important, that so the heat transfer we have discussed. So what are the different factors, what are the different effects which influence the heat transfer inside the cylinder? So we will quickly revisit the different factors, different effects which are influencing the heat transfer. So the effect of, I can say, engine operating variables on the heat transfer. So this is quite obvious that we have discussed about that there will be three different modes of heat transfer. At least we should know that now engine is running. So will these modes of heat transfer will these modes of heat transfer depend on the engine size? Will these modes of heat transfer depend on the engine speed and also the load? These three important points you need to keep in mind, that the engine size, engine speed and the load. So we have discussed about these three different modes of heat transfer. We have understood it. At least now time has come to know whether these three different modes of heat transfer can be affected by altering the size of the engine, load of the engine as well as the engine speed. So we will discuss now the effect of engine size. So what will be the effect of engine size? See, we have, again I am telling that if we try to recall that when we talk about heat transfer from the engine, if we now try to look at the schematic depiction over here, so if we increase the surface area of the engine, then definitely heat transfer will be increased. At least the convective heat loss to the ambience will be increased. So the convective heat loss to the ambience, this part will depend upon the convective heat transfer coefficient, surface area into TW2, that will depend upon convective heat transfer coefficient, surface area and TW2 minus TA. So at least if we can increase A, then rather we can say the heat transfer rate will be enhanced. So if engine size is getting, if the engine size becomes higher, then heat loss will be higher. That is what we have understood. So important point is note, that means if we have two geometrically similar engine of different size, geometrically similar, I can say engine of different size, that means geometrically similar in shape but not in size. So that is called geometric similarity. That is what we have studied in our fluid mechanics course. What do you mean by geometric similarity? They are identical in shape but not in size. So if we now consider two different engines, they are geometrically similar, that means their shape is similar but size may not be similar. So if this is the case, then we have understood that if we try to increase the size, surface area will be increased without compromising if we increase the size, definitely efficiency will be increased. The mass flow that we are taking per stroke, that will be increased. So combustion rate will be increased, efficiency will be increased. So what we would like to say, that if we increase the size of the engine, then the surface area will be increased. So at the same time we are, the heat transfer rate will be increased. So if we try to write that, so larger engine will have, greater heat loss, but will be, thermally efficient, will be more thermally efficient. That means if you increase size, the mass flow rate of the fuel, mass flow rate of the air fuel mixture that is drawn into the cylinder will be increased, stroke volume will be increased, but that means that will increase the thermal efficiency, but at the same time we will have greater heat loss. Next is engine speed. Now, what is the effect of engine speed? Again we need to, recall our fluid mechanics knowledge. If we increase the engine speed, that means the velocity of the combustion gases inside the cylinder will be enhanced. It will be more chaotic kind of, flow situation. So if the flow velocity increases, the velocity of the combustion gases inside the cylinder is getting increased, definitely heat transfer rate will be increased. So higher the heat transfer rate from the combustion chamber, from the engine cylinder into the wall, and that higher heat transfer rate will promote higher heat transfer to the ambience. So in a way we can say the engine, if we increase the engine speed, the rate of heat transfer, that is convective transport of heat, will be increased. So I am writing that if the speed is increased, gas flow velocity will increase, and consequently the heat transfer rate will be increased. So that is what we have seen. And finally we need to know what is the load, that is the effect of engine load on the heat transfer. So engine load, we need to increase load, that means the demand from the engine, engine needs to supply more work output. That means engine is, going to uphill, or it is pulling a trailer. So if a trailer is connected to the engine, or engine is going to uphill, so in these two cases the engine load will be increased. So now if engine load is increased, what we need to do? That is what we have seen from the electronically controlled unit. That means depending upon the sensor of the, whether the engine is going to uphill or the trailer is connected to the engine, the throttle valve position, that means electronically controlled unit will, send response to the throttle valve for the complete opening. If now throttle valve open completely, pressure drop will be less, frictional effect will be less. So what will happen? Then mass flow rate which is drawn into the engine cylinder will be higher. If the mass flow rate higher, heat transfer rate will be higher. So I am writing now that as the load is increased, throttle valve is fully closed, fully open. mass flow of the, I can cite mass flow rate. Air and fuel will be higher, and heat transfer associated with I mean, I can write heat transfer in the engine. I can write heat transfer in the engine, we will discuss now, will be higher. So, this fellow H into A into delta T will be higher. By how? So, see this heat transfer, convective heat transfer coefficient, which is proportional to Reynolds number. Now, if we keep on increasing, rather if we increase the mass flow rate by opening, gradually increasing the throttle opening area, then mass flow rate will be higher. The higher mass flow rate will try to increase the higher Reynolds, will leads to higher Reynolds number, flow velocity. So, if Reynolds number becomes higher, then the convective heat transfer will be coefficient will be higher, which in turn will increase the heat transfer rate. So, that is what I mean we have discussed. So, that means we can say that as the load increases, that is very often required, I mean very often engine will very often face this situation. That means engine is going uphill, or sometimes a trailer is connected. Then what will happen? The electronically controlled unit will send response to the throttle valve to increase the opening area. Now, once the opening area is increased, mass flow rate of the air and fuel will increase. Higher the mass flow rate, Reynolds number will be higher as the flow velocity will be increased. So, now as Reynolds number increases, convective heat transfer coefficient will be increased, which in turn will increase the heat transfer rate. So, to summarize today's discussion, we have seen that the power output of the engine, which is not equal to the power developed at the piston face. We have discussed and we have tried to discuss through the quantitative description that how much portion of the energy is getting converted into the shaft work, while remaining part of the energy is getting lost. Remaining part of the energy is getting lost, that means the remaining part is not getting lost to the ambience, some part is getting lost, some part is getting used to overcome the parasitic loads and other things. So, we have seen that some part of the energy is getting lost to the ambience, that means the heat is getting lost. Heat is the form of energy which is getting generated because of this combustion reaction. So, what are the different modes of heat transfer and heat transfer mechanism inside the cylinder, that is what we have discussed in detail, and we have finally seen that what are the different factors that is we have discussed that engine operating variable, effect of engine operating variable on the heat transfer rate. So, and we have discussed that this heat transfer rate should be there essentially to save the engine out of excessive heating of different parts, as well as to save the lubricating system properly. On the other hand, the transport of heat from the cylinder to the coolant should not be substantial, otherwise thermal efficiency will reduce drastically. So, with this I stop my discussion today, and we will continue our discussion in the next class. Thank you.